Well, we've talked about enumerative data, looking at all the data. We've talked about analytic data, seeing it in time series. We've talked about this idea of central tendency and also deviation. Now what I'd like to do is put all of this together so we can understand what data is actually telling us. And so we want to do this using our expression y is a function of x. So we see that y is actually going to be a function of a number of x's that contribute to a process. And as we go through that process, we see this f's themselves, f of x, may actually turn into a new y, and it may be composed of a whole bunch of x's. So to give an illustration of this, so when my daughter was young, she wanted to have a lemonade stand. And so we had an understanding that there probably wasn't too many neighbors. There were only 3 houses beyond us in the summer cottage that people weren't even living there. So she probably wasn't going to be making a whole lot of money. So I decided to turn this into an exercise where she should learn something valuable. So we thought about teaching her y is a function of x. And of course her question was why? Okay, so y is a glass of lemonade. So I asked Krista, I said, what goes into this? What are the x's? She said, what do you mean? I said, well, what is the recipe? And she said, oh, how do I make lemonade? Yeah, that's it. So she said, okay, well, there has to be a lemon ingredient. We have to have some amount of sweetener or sugar. We have to have water and ice. And that's pretty much it. Okay, what type of lemon ingredient do you want to have? Realizing now we're going to take the first x and open it up and inquire about it. So she said, well, there's a lot of options here. We could have fresh squeezed lemon. We could have liquid concentrate, we could have frozen concentrate, or powdered lemon flavoring. I said, well, what will you choose? She said, I'm a vegetarian. I want the fresh squeezed lemon. I said, okay, well, what is it about that fresh squeezed lemon, realizing now that this X is being opened up into another set of rational subgroups for us to understand what's going on? So she said, well, I don't want finished lemons because finished lemons never get sweet. They stay hard. They're like baseballs. So I want to care about, I'd like Spanish or Portuguese lemons. And then I have to worry about how they were transported here. Did they get here fast enough? And then how old was the lemon when I squeezed it? And then maybe how I squeezed it. And you see, what we've done now is we've taken y as a function of x and further refined it and refined it and refined it some more. This is like going on a walk on the Gemba. And in each step, we've gotten another idea of rational subgroups, of possibilities of things that will make a quality difference to the lemonade. So what happens in a process is, at the work level, we have these measures, quality, cost, and time. At the business level, we're going to convert them into some formula to estimate what is the performance of the process. And y is a function of x will be a function of quality, cost, and time. And then we make a consolidation of those y's, and we turn the language then from the reporting structure at the base level into some sort of financial measurement system that we use for the financial rules that express what is the expectation of financial performance for the system. Now, when we look at the normal distribution, this is the distribution most of you were taught in school if you took statistics. And we see that the area of the curve is always equal to 1. And it goes from 0 to 1. And underneath that curve, we have all of the data. And so we see a histogram created that way. And so we can see that based on this formula, we can have an equation to express it. And we see based on the amount of standard deviation, we can talk about how peaked it is or how consistent it is around the mean. If it gets flatter, it's less consistent. But the shape of the distribution always stays the same. It's this bell-shaped curve. Now, if we take a look, the standard normal distribution, we have this probability, and we can see it in terms of these different shapes, and we can also express it as a cumulative distribution, which looks like an S-curve. Now, this is all great for a mathematical statistician, but when we go in the real world, we don't really see those types of distributions. We see a lot of other messes. But there is a rule that's important for us to take a look at when we go observe data. And that is called the empirical rule. And this is true of all distributions. If I go take a look at a data set, 68% of all data in any type of statistical distribution is within one standard deviation of its mean. 95% approximately is within 2 standard deviations, and 98.7% is within 3 standard deviations of the mean. So if we take a look at our distribution, this would be the expected performance that we would see in terms of the distribution of the data. Anything outside of that distribution would be an unusual observation. Now we look at data, we see there are different types of data distributions. So we see three here. One is the symmetric distribution. And here it's peaked in the center and it's tailing off in the sides. That would be typical of a normal distribution. We would get this type of performance in a process if what we want to have is the central tendency. For instance, on-time delivery or on-specification measurement of something like length. And we have then plus or minus so many centimeters, but we would expect that to be distributed around that. Now another distribution, we can see it's called this negative skew. And in the negative skew distribution, what we have is a tail going off to the left. And this occurs if we have a scale where we want to achieve something at the high end. So for instance, we would like to have not on-time delivery, but we'd like to have, say, high productivity. So productivity, we're going to drive towards 100%. So the deviations or the bad things are when it's low. And so this would be a negative skew tail. A positive skew tail happens when we have the opposite. So for instance, we would like to have short cycle times. So long cycle time events are going on the tail to the right, and those would be the negative events. And so we can see when we take a look at the individual measures, we can understand goodness or badness of the measurement based on what that measure is and the expected performance we'd like to see it achieve. Now if I take a look at some data, I say here are 25 data points in 9 different distributions. Can you tell me what type of distributions they are by just looking at them? Well, most of us probably can't, but I'll give you a hint. They're all actually normal distributions. But the problem is the naked eye can't really see the normal distribution in there, whereas mathematically we could calculate it. So what happens? We can create what's called a normal probability plot. And this is plotting now the observed data, each of those dots, versus the actual normal distribution, which is this straight line in the middle. The dashed lines around each side of it are 95% confidence interval that this is fitting a normal distribution for the data we have. And what we see is all of the data is within the dashed lines. It's within the 95% confidence interval. So even though the data looks kind of ragged and it moves around a lot, we would say that we could treat this data as a normal probability distribution. So if we look at the data that we just saw about those 9 different displays of 25 data points, what we see is all of them show up looking like a normal distribution. They're all within the 95% confidence intervals. So as I take a look, I said, wow, there's an interesting thing. If I show this data in a different graphical representation, I can rapidly get to the choice of what type of distribution it is. So that's important to us. So if I look, distributions will have classical shapes. And we look at them in probability plots, we can actually see the way those plots will display when we show the raw data versus the probability data, and then we can interpret that information. Now the reason that we do this is because we would like to be able to make some rapid judgments about what's going on in the data over time. So for instance, let's do a little exercise. Here we see 2 data sets. The black is the expected or desired performance, and the green is what we actually achieved. What's the problem? Can you tell? So we'd like the data to be here, and the data's up here. Now notice the bandwidth, it's about the same. They're both about the same width. If we look at it in the summary view and a probability, they're both shaped like a normal distribution, but the green one is off. So the problem here is I need to shift the green one to the black area, which is the desired level. So now I understand something about the process. The behavior we want to have to improve the process is to find some factor that will shift the mean. Now I know what I'm looking for when I'm going on my Gemba walk and looking at the process. Here's a different process. Now we see the black is narrow, but the red is evenly distributed around it. And what we see is that we look at the summary view, we see, the red distribution and the black distribution have the same central tendency, but black is flatter. So what's the problem? If we want to move the red distribution to the black, we have to reduce the variation. So this type of problem says we're going to look for factors that will actually reduce variation in the process performance. So which of the x's have that capability? Again, we have another hint. And finally, the third one, we see here there's the blue distribution. It's shifted off and it's wider. So the solution for this is, what can we actually do to shift the mean and reduce the variation? Now, one of the fastest ways to do this is to take a look at that lower tail on the blue distribution and find out what's in there. That's the wow. That's the worst of the worst. And over here we have Bob, the best of the best. What was the process doing there? Can we shift all of those wow factors in the process to the Bob factors, and then we shift the mean and reduce the variation all at once? So this is the practical engineering solution we go about. So we take a look at our distribution, and we're going to categorize the performance in terms of different ways that the process is physically operating. In some of those rational subgroups, it's delivering category A, reasonably good performance. Some are delivering category B and some category C. And what we want to do is get rid of the category C. Start cutting off all of those events that are in rational subgroups that elongate the performance and take us away from the desired state we have. And this is what we want to do as we're going on our search for the variables. So we want to be working smarter, not just working harder. We want to figure out what is it in our process that's going to cause the change to happen that will drive the process and shift it towards the desired state of performance for our target. What we're going to do next is we're going to take a look inside Minitab. We're going to give you some familiarity with it to understand how you can do some of the things that we've been talking about at the greenbelt level of performance.